Hello guys and welcome to another past question review. We are going to look at a question in state space analysis. Now, let's dive into the question. So it can be proved that the relationship between the current I passing through an inductor and the voltage across it in parallel with the capacitor and resistor is given by this state equation over here, I dot v dot equal to, we have our state matrix over here and we have our state variables I and v. So they want us to solve for I of t and v of t, given that L equal to 1, C equal to 1 over 5, 1 over CR equal to 1 over 2. So let's dive into the solution of this problem. So the first thing we are going to do is we are going to substitute these values that are given to us into this state matrix so that we can get something like this. So we have I dot v dot will now be equal to substituting, we'll have 0, so minus 1 over c, so minus 1 all over 1 over 5, and you now have 1 over L, that's 1 over 1, and you now have minus 1 over CR, that's minus 1 over 2, okay. Since CR is 1 over 2 itself, then you will have IV like this. So our aim is to solve for what? I of t and v of t. So if you resolve this, you're going to get I dot v dot is equal to, you will have 0, 1, 1 divided by 1 over 5. That's you have negative 5 if you take account of the negative sign, and you have negative 1 over 2 over here, and you now have your I and you have your v like this. So this is where we are at this point. Now the equation, the system above is equivalent to we have an x dot of t is equal to a x of t. Okay, so our system is equivalent to a system like this, and anytime we have a system like this, the solution of this system s of t is given by some eigenvector v, then exponential lambda t. Okay, so some eigenvector v exponential lambda t, and this will certainly expand to, let's say for a 2 by 2 system, it's going to expand to c1 exponential lambda 1. Then we now have our first eigenvector, that's our v1 exponential lambda 1 t, sorry, and plus c2 exponential lambda 2 t, then you now have your what? v2. So this is an arbitrary constant. C1 and C2 is an arbitrary constant. Lambda 1 is the first eigenvalue, and lambda 2 is the second eigenvalue. Then lambda v1 is the eigenvector that is associated with lambda 1, and v2 is the eigenvector that is associated with lambda 2. So with this, we'll be able to get the solution of this system. Okay, so anytime you have a system given to you like this, okay, then these are homogeneous system of equation, then you have to express your solution in this form where v is an eigenvector. Some people write v dash or v like this just to show that it's a vector, but I'm just going to make it tick so that you know it's a vector. Then you now have your lambda for eigenvalue, then you now have your t. So this solution is going to split to what we have here. So these are our independent solutions for this 2 by 2 system. Now we are going to begin right away. So to solve this problem, we see that we need to find our eigenvalues. Okay, we need to find the eigenvalues for this system. So when we are given this particular system, our I dot and V dot like this. We have 0, you now have minus 5, and you now have 1 and minus 1 over 2. You now have your I and V. You need to determine eigenvalues. So determine eigenvalues. So if we determine our eigenvalues, then we will actually have to use this matrix, which I'm sure you're familiar with, A minus lambda I, okay, V equal to 0. So this is the central definition that helps us, or this is what we call the eigenvalue problem. So you always make reference to this particular equation like this when you want to determine your eigenvalues. Of course, it comes from the fact that every eigenvalue satisfies A times V equal to lambda times V. So this is your state matrix. Okay, so there is a particular vector upon which, when you multiply E by that particular vector, it's still the same thing as multiplying a scalar lambda times that vector. So this vector is called an eigenvector, and this is an eigenvalue. Okay, anything that satisfies this condition. So if you subtract like this, you get 0, and if you factor out V, you get V minus. Since you're factoring V from a scalar, you need to introduce your identity. So minus lambda I V equal to 0. So that's where this equation comes about. So you always make use of it when you're solving this kind of equations. Now the next thing to do is to find your characteristic equation. So our characteristic equation is going to be this determinant A minus lambda I equal to 0. So this is our characteristic equation. So the characteristic equation helps us to determine what we call our eigen values. So from this particular matrix, our A is actually given to us as, we have 0, you have 1, then you now have minus 5 and minus 1 over 2. Then minus lambda identity is going to be in this case 1 0 0 1. Okay, so you're solving this determinant and you're equating it to 0. So if we solve, we're just going to get this 0 1 minus 5 minus 1 over 2, then minus we have lambda 0 0 lambda. Okay, we're solving the determinant equal to 0. So when we solve further, we're going to get 0 minus lambda giving me minus lambda. 1 minus 0 is 1, minus 5 minus 0 is minus 5, and minus 1 over 2 minus lambda gives you what? Minus 1 over 2 minus lambda. So you're going to solve this and equate it to 0. So typically what you just need to do is that anytime you're given your A matrix and you want to find the that's A minus I lambda matrix, all you just need to do is just subtract lambda from the diagonals, the leading diagonals of that particular A matrix. So this is your A matrix or your system matrix. Is that okay? So we're going to continue from this point on. So we are going to solve this particular matrix, evaluating the determinant and equating it to 0. So this times this minus this times this. So you have minus lambda times minus 1 over 2 minus lambda. Okay, then minus 1 times minus 5, which is going to be a minus 5, equal to 0. Is that okay? So if you rearrange this one, you have minus lambda into lambda plus 1 over 2. Okay, I just factored out the minus sign from these two places, and plus 5 equal to 0. So this minus sign can cancel out this minus sign. You have lambda into lambda plus 1 over 2, and plus 5 equal to 0. So you can decide to solve this particular equation given the circumstances. In an exam scenario, you could easily use your calculator, your scientific calculator, to evaluate the eigenvalues. Okay, I don't think there is a crime in using your scientific calculator, since they are not really interested in your ability to factorize, especially when you're dealing with three polynomials in degree 3. So if you can use your scientific calculator to determine the roots of this equation in this scenario, good and fine. But since I don't have a scientific calculator here, I'll just try to use method of completing the square. So lambda square then plus half lambda will be equal to minus 5. So lambda square plus half lambda, so we need to add half the coefficients of lambda square, that's 1 all over 4 squared to both sides, minus 5 plus 1 all over 4 squared. Then this will now transform to lambda plus 1 over 4 all squared is equal to, so when you solve this, you get minus 5 plus 1 over 16, which evaluates to minus 80 plus 1 over 16, which is negative 79 over 16. So when you solve, you're going to get lambda plus 1 over 4 all squared is equal to negative 79 over 16. The implication is that lambda plus 1 over 4 is equal to plus or minus the square root of minus 79 over 16, and this translates to plus or minus I root 79 all over 4, because the I is coming from this, and the 4 is coming from the square root of 16. So it implies that our lambda plus 1 over 4 is equal to plus or minus I root 79 over 4. Therefore, our lambda is equal to minus 1 over 4 plus or minus I root 79 over 4. So this is a complex eigenvalue, okay? Complex eigenvalues. So we're going to continue. So we got at our lambda is equal to negative 1 over 4 plus or minus I root 79 over 4. So this means that lambda 1 is equal to minus 1 over 4 plus I root 79 over 4, and lambda 2 is equal to minus 1 over 4 minus I root 79 over 4, like this. So these are our two eigenvalues. Anytime you get a complex eigenvalue, that complex eigenvalue is actually taking care of two, because you have the complex value and its conjugate. So the complex value is 1, then its conjugate is another eigenvalue. Is that okay? So two eigenvalues for a 2 by 2 system. Now that we have these eigenvalues, the next step is to determine the eigenvectors. So to determine the eigenvectors associated with each of these particular eigenvalues. Now let me tell you something about complex eigenvalues. Now when you have a complex eigenvalues, if you want to find the eigenvector associated with them, you just need to work with only one of the complex eigenvalues. Okay, so if you work with one of that complex eigenvalues, from that one you can get the second one directly, so you don't need to solve for this one. So if I start finding the eigenvector of this one, the eigenvector of this one will lead me to the eigenvector of this one, because the eigenvector of this one will be a complex conjugate of the eigenvector of this one. So if I find the eigenvector associated with this guy here, I'll just know that the eigenvector for this one is the conjugate of this guy, the vector conjugate, okay, of this guy. So let's see how it works. So for complex conjugates, remember, you don't need to solve for two eigenvectors, you're just solving for only one, then that one will lead you to the other one. Now follow me very carefully. So to determine the eigenvectors, we have to use this equation a minus I lambda, okay, then v equal to 0. So this is the equation that we are using to determine our eigenvectors, and we remembered that this translated us to minus lambda 0, we have minus 5, and minus 1 over 2 minus what? Lambda, if you can still remember. So we now have our v is equal to what? 0. So this is a 0 vector. This is your eigenvector that you want to find. So we're going to start solving, all right, step by step. So we're going to say for lambda 1 equal to negative 1 over 4 plus I root 79 over 4. We are going to have this transforms as minus into minus 1 over 4, okay, and plus I root 79 over 4, and you now have 0, and you now have minus 5, and you now have minus 1 over 2 minus minus 1 over 4 plus I root 79 over 4. Is that okay? So you will have your eigenvector. Now we can make our eigenvector. Let me call it v 1 1 and v 2 1. Okay, then you now have equal to 0. Your 0 vector is 0 0, like this. Is that okay? So you can actually now say for this particular one, you will have 1 over 4 minus I root 79 over 4. When you open with the negative sign, then you now have minus 5, and you have 0 here. Then if you open this one, you get 1 all over 2, and you now get plus 1 over 4 minus I root 79 over 4, and you have your v11 v21, then you now have 0 0, like this. So we want to determine the value of v11 and v21. Okay, so we'll have this 1 over 4 minus I root 79 over 4 and minus 5, then you now have 0. So minus 1 over 2 plus 1 over 4, okay, it's just like saying minus 0.5 plus 0.25. Minus 50 plus 25 is going to give me minus 25, which is going to still be minus 1 over 4. Okay, so this and this gives you minus 1 over 4. Then you now have minus I root 79 over 4. Okay, and you now have v11 v21, and you now have 0 0. Now whenever we are working with complex eigenvalues, we need to be very careful. Usually we can actually perform row operations to simplify the procedure for us. So this is how I'm going to perform row operations. I'm going to augment my matrix like this: 1 over 4 minus I root 79 all over 4, and you now have 0. So I'm going to augment this matrix. Here is 0 0 with this particular one over here. Then you now have minus 5, then minus 1 over 4 minus I root 79 over 4. So you will observe that I can now perform some row operations. I want to convert this matrix to something like a row echelon form or a reduced row echelon form. So if I convert it to reduced row echelon form, it will enable me to obtain the relationship between v11 and what? v21, which are the values that I want to get from this particular system of equation. So how do we do that? The first thing is I'll divide this particular term. So I'll say my new row 1 is equal to the old row 1 divided by this term. So 1 all over 1 over 4 minus I root 79 over 4. Okay, so I'm dividing the old row 1 by this particular term. Okay, so I can also say that my new row 2 is equal to old row 2 divided by minus 1 over 5. Okay, so let's see how this will transform our system. So in the new row 1, we are dividing each term by this particular value over here. So when you divide this term by itself, oh, is this a 0 or is this a 1? Okay, this is meant to be a 1. I'm sorry, I'm making a mistake, so just quickly correct it to 1. It's been a 1 all this while. So you have 1 1 1 and 1 like this. So sorry for that mistake. Then you have a 1 all this while. So now that we've gotten the backtrack, so let's divide now. So when we divide, we're going to divide this by itself. So this term divided by itself is going to give you 1. So you will have 1 divided by 1 all over 4 minus I root 79 over 4. And you now have 0 divided by that term, which is still going to be 0. Okay, you have 0 and 0 here. So because 0 divided by anything is 0, so minus 5 divided by minus 5 is going to give you 1. Then minus 5 divided by this term divided by minus 5 is going to give you minus 1 over 4 minus I root 79 over 4 divided by minus 5. Is that okay? So, and definitely 0 divided by minus 5 is going to be 0. So at this point, we want to evaluate what this particular value is. So let's try to evaluate it and see what we are going to get. So what is 1 divided by 1 all over 4 minus I root 79 over 4? So for those of you that have a scientific calculator, you could decide to do that. But if you're good with complex conjugates, you can easily take a conjugate and multiply it up and down like this. 1 over 4 plus I root 79 over 4 divided by 1 over 4 plus I root 79 over 4. Okay, so when you simplify, you're going to get 1 over 4 plus I root 79 over 4 divided by, so when we multiply this term by this term, remember when you multiply two complex conjugates, you're going to get a real number. So that is the sum of two squares. So this and this will give you 1 over 4 square, while this and this will give you plus root 79 over 4 squares. So there's what we call difference of two squares and sum of two squares. Difference of two squares is x squared minus y squared, giving you x minus y and x plus y. But in the world of complex numbers, the sum of two squares, x squared plus y squared, is actually taken as the difference of two complex numbers, x minus iy and x plus iy, like this. So that's why this will result in this term. So let's see what we get when we add 1 over 4 squared plus root 79 over 4 squared. 1 over 4 squared, then plus root 79 4 squared, like this. So sorry. Okay, we get exactly 5. Is that okay? When you add these two terms, you're gonna get 5 exactly. So that is going to give me 1 over 4 plus I root 79 over 4 divided by 5. So that is what we get when we take the reciprocal of this complex number over here. So I'm just going to write that at this point in the new line. We are going to have 1. Then the reciprocal of that complex number above give us 1 over 4 plus I root 79 over 4 divided by 5. Then you now have here is 1. Then now look at these numbers carefully. You can figure out that if you cancel this minus sign throughout, or if you factor out the minus sign and if you cancel, what you're going to be left with is you'll be left with 1 over 4 plus I root 79 over 4 divided by 5. Okay, so it's exactly what you'll be left with when you cancel out with this minus sign. Is that okay? So you will have 0 and 0 here. So we can see now that row 1 and row 2 are exactly alike. So to finish up our row operations, we can just say new row 2 is equal to old row 2 minus row 1. Okay, so we are going to subtract all the entries in row 2 from row 1. So that is going to give me this. So uh we're going to say row 1 will remain as it is. That's 1. Then if I simplify this particular 1 all over 4 plus I root 79 over 4, I will get something like 1 all over 5 divided by 1 divided by 4 plus I root 79 over 4, like this. So I can have it like this, then 0. So these are row 1 remaining the way it is. Then row 2, what will happen to row 2? So 1 minus 1 will give you 0. And finally, this term minus this term, since they are exactly alike, it's going to give you 0 too. So you've converted your matrix into reduced row echelon form or row echelon form. So this now gives us an edge. As we can see, if we write it again back in the form, we know we'll have 1 and distribute this 1 over 5, you're going to get 1 over 20 plus I root 79 all over 20, like this. And you now have 0 0, and you now have your v11 v, okay, 2 1, and you now have 0 0. So this makes it easy for us to say that v11, okay, when you open the bracket, 1 times v11 is 1, then plus 1 over 20 plus I root 79 over 20 into v21 is equal to 0. So with this, we can find a relationship. We can simply say that our v11 is equal to negative 1 all over 20 plus I root 79 all over what? 20. And you now have what? Your v to 1, like this. Is that okay? So we've gotten this. So we can now see, let me just make a small line here. When v21 is minus 1, for instance, when v21 is minus 1, when you plug in minus 1 into this place, you're going to get v11 is equal to minus 1 over 20 plus I root 79 all over 20. Then you now see minus 1. Then the minus will cancel out the minus. Then v11 is going to be what? 1 over 20 plus I root 79 over 20. So typically in eigenvalues and eigenvectors, you could actually choose any number that you want. It's actually infinite solutions. Okay, infinite solutions. There are infinite eigenvectors for every set, but we want to go with the base form. So the base form. So the base form is when we select numbers like 1, minus 1, and all those small numbers, so that when we give the number to one quantity, we could easily identify the other quantity. So when v21 is minus 1, v11 is equivalent to this guy that you see over here. So we've gotten our eigenvectors. We're going to write them up here. Okay, for our eigenvalue, lambda 1 equal to minus 1 all over 4 plus I root 79 all over 4, we obtained our eigenvector, that's v to be this value. We have 1 all over 20 plus I root 79 all over 20. Then we now have minus 1. Okay, so I believe this is what we obtained down here, as we can see. So we are going to now wrap up this problem like this. Sorry about that. So to wrap up this problem, we have to first of all understand that normally when you're solving these kind of questions, when you solve the eigenvector associated with one particular eigenvalue, you have to solve for the eigenvector associated with the other eigenvalue. But since we're dealing with a complex number, now we're dealing with complex eigenvalue, you have to understand that our second eigenvalue, which is minus 1 over 4 minus I root 79 over 4, which is the conjugate of the first eigen value, is going to have, in theory, its own eigenvector to be the complex conjugate of the first eigenvector, which is 1 over 20 minus I root 79 over 20, and you now have minus 1. Yes, I'm not changing this to plus 1 because you cannot take the conjugate of a real number. Okay, so you only take the conjugate of an imaginary number. All right, that you just swap the negative sign of, or the coefficient of I. If it's positive, you change it to negative, and if it's negative, you change it to positive. So let's have it at the back of our mind that for complex conjugate, or for complex eigenvalues, we just need to solve for only one eigenvector, then the other eigenvector will be the complex conjugate of the first one. So I'm going to base my focus on this particular system. I want to finalize the solution of this problem now. Okay, so remember that we have our solution x of t to be in the form, we have v exponential lambda what t. Okay, so this is like the general form of the solution of our system. So one possible solution to this system, okay, is going to be x of t is equal to, you can leave the arbitrary constant for now, so you can just put exponential lambda 1 t, and you now put the eigen vector that we just computed, which is 1 over 20, then plus I root 79 over 20, and you now have minus 1. So this is one possible solution to this system, and it is equivalent to exponential. We have minus 1 over 4, okay, then plus I root 79 over 4. You have c, and you now have this vector 1 over 20 plus I root 79 over 20, you now have minus 1. So this is one possible solution. And remember that this x of t is a matrix. It's actually a vector that contains our I of t, that's our state variables, and v of t, which we are interested in finding. So let's take note of that. So we are going to solve for x of t. So let's analyze this solution and see what we get. Now, whenever you're dealing with complex eigenvalues, when you analyze one solution, you can be able to use that one solution to get the general solution of the system. And that's what we are going to do with this arrangement over here. So we have our x of t to be, let me see, we have, okay, now at this point I can just expand this bracket and apply law of indices. So what I'm going to get is exponential minus 1 over 4 t dot exponential I root 79 over 4 t. Okay, I hope we understood the expansion. T, you distribute the t, then you use law of indices to separate the exponential as exponential a plus b is exponential a dot exponential b, like this. Okay, so let's take note of that. So we now have our vector, which is 1, okay, over 20, then plus I root 79 over 20, and you now have a minus 1. So at this point, you're going to recall that exponential I theta is cos theta plus I sine theta. Okay, so this is our Euler's identity. One of Euler's identity. So we're going to apply it to this particular value over here. So our x of t will now be exponential minus 1 over 4t. And when you apply Euler's identity on this one carefully, you're going to have cos root 79 over 4t plus I sine root 79 over 4t, like this. And you now have the vector, which is 1 over 20 plus I root 79 over 20, and you now have minus 1 like this. Then what we are going to do is we are going to what, expand. Okay, we're going to expand like this. So we are going to have x of t is going to be exponential minus 1 over 4t. Okay, then when you use this one to multiply these two terms, you distribute it to these two vector terms, you're going to have something like this: cos root 79 over 4 I, okay, sorry, t, this is a t, then plus I root 79 I sine root 79 over 4 t multiplied by 1 over 20 plus I root 79 over 20 like this. Then this term times this one is going to be minus cos root 79 over 4 t. Then you now have or let me just call it plus I, then minus sine root 79 all over 4t. So there's a reason I placed it like this. You just expanded these terms with minus 1. So I collected it like this for a particular reason. So I'll show us later. Now that we have it like this, our objective is to try to separate the real parts and the imaginary parts. Okay, so we want to separate the real parts and the imaginary parts of this particular arrangement. So we are going to expand and collect all the real parts, and we're going to collect all the imaginary parts. So x of t is going to be exponential minus 1 all over 4t, and into, when you expand this term times this term, is going to give you 1 all over 20 cos root 79 all over 4t. So another thing that can give me a real term is when I multiply these two imaginary parts by each other. So I times I, very good, I times I gives you I square, and I square is minus 1. Okay, so we now have this term, and this term will give me minus 1, or minus sine minus root 79 over 20, then sine root 79 all over 4t. Okay, so I times I is an I square, then this term is root 79 over 20, and you now bring your sine root 79 over 4t. Okay, so this I square becomes minus 1, and you now have minus 1, then root 79 over 20, then sine root 79 over 4t. So that's how I got this term over here. So when you expand, what can give you imaginary? This term times this term gives me imaginary, giving me plus I, okay, and 1 all over 20. You now have sine root 79 over 4t. Then this term and this term and this term finally will give me another imaginary, this and this. So when you multiply them together, you get plus I root 79 over 20, then cos root 79 over 4t. Okay, so this is the expansion. Then for this particular one, you already have minus cos root 79 over 4t, and you now have plus I into minus root, sorry about that, I into minus sine root 79 all over 4t like this. Then when we collect all the real and imaginary parts, we'll have our x of t to be equal to exponential minus 1 all over 4t into, collecting the real parts, you will have 1 all over 20 cos root 79 over 4t minus root 79 over 20 sine root 79 over 4t. Okay, the real parts plus imaginary parts, I bracket, you have 1 over 20 sine root 79 over 4t, then plus root 79 over 20 cos root 79 over 4t, like this. Then you have this as the real part, giving you minus cos root 79 over 4t, then plus I. You now have minus sine root 79 over 4t, like this. So let's be careful here. At this point, this single vector can be separated into two vectors, because by theory, a plus b, c plus d as a single vector can be splitted into a, c plus b, d. Okay, so that's what is going to happen here. And take note of this term while we are doing the separation. So x of t will be exponential minus 1 over 4t to be distributed to the first part, which is the real part. So we have the real plus, we now have our exponential minus 1 over 4t, and we now have the imaginary. Okay, so this is how we are going to separate this stuff, like this. So x of t is going to be exponential minus 1 over 4t. Now the real part of our equation is going to be, I'm going to try to squeeze it. So we have 1 over 20 cos root 79 over 4t, then minus root 79 over 20 sine root 79 over 4t. Okay, so this is the real part. Then you now have minus cos root 79 over 4t. Okay, and we now have plus the imaginary parts. We have exponential minus 1 over 4t. Then you now have I into the imaginary vector, which is 1 over 20, and sine root 79 over 4t, and plus root 79 over 20 cos root 79 over 4t. So pardon me for that. And you now have minus sine root 79 over 4t, like this. Okay, so you can see that we have converted from this particular system to two separate systems. Now at this point, you can take this as your solution, but we need to generalize. We can generalize these two separate solutions as a system comprising of an arbitrary constant c1, and you now have exponential minus 1 over 4t, and into the first vector is 1 over 20 cos root 79 over 4t, then minus root 79 over 20 sine root 79 over 4t. Okay, then plus you have minus cos root 79 over 4t here. So plus, so instead of you to have I, you can just call an arrangement at random that's take an arbitrary constant. Then you have c2 exponential minus 1 over 4t, and you now have 1 over what, 20, then sine root 79 over 4t. Okay, then plus root 79 over 20 cos root 79 over 4t over here. Then you now have minus sine root 79 over 4t, like this. Is that okay? So the after separating it into the real and imaginary part, the next step is to generalize the vector by adding your arbitrary constant. So in adding arbitrary constant, you can do away with your imaginary number I, because I is also a constant. Okay, so once we have it like this, the next step is to recall that our x of t is equal to what? I of t and v of t. Okay, so we can actually see that I of t, v of t vector will be equal to c1 exponential minus 1 over 4 t, and you now have 1 over 20 cos root 79 over 4t, then minus root 79 over 20 sine root 79 over 4t. You now have plus c2 exponential minus 1 over 4t. Here is a minus cos root 79 over 4t, and into this vector 1 over 20 sine root 79 over 4t, then plus root 79 over 20 cos root 79 over 4t, like this. And you now have minus sine root 79 over 4t. So you can now see that since you have this arrangement like this, it becomes easy to conclude that I of t, therefore I of t will be everything on the first row, and v of t will be everything on the second row. So I of t is c1 exponential minus 1 over 4t, okay, and into 1 over 20 cos root 79 over 4t, then minus root 79 over 20 sine root 79 over 4t, okay, like this. Then plus c2 exponential minus 1 over 4t into 1 over 20 sine root 79 over 4t, then plus root 79 over 20 cos root 79 over 4t. So this is I of t, and v of t is going to be what? From this same arrangement, you're going to have c1 exponential minus 1 over 4t. So you use this to open the second row, and you're going to get c1 exponential minus 4t, then into minus cos root 79 over 4t, and you now have plus c2 exponential minus 1 over 4t, and into minus sine root 79 all over what? 4t. So basically your v of t is equal to minus c1 exponential minus 1 over 4t cos root 79 over 4t, and you now have minus c2 exponential minus 1 over 4t, and you now have sine root 79 all over 4t. Okay, so if you have it like this, since these are arbitrary constants, minus c1 can be equivalent to d1, and minus c2 can be equivalent to d2. So we can have our v of t finally to be d1 exponential negative 1 over 4t cos root 79 all over 4t, then plus d2 exponential minus 1 over 4t, then sine root 79 over 4t. Or if you want to be more professional, you can say exponential minus 1 over 4t brackets d1 cos root 79 over 4t plus d2 sine root 79 all over what? 4t. So these are the time domain solutions of our v of t and our I of t. Okay, and you can be able to find this arbitrary constant if you know the initial condition of your system. So with this, we've come to the end of this particular problem. So summarizing the steps is, first of all, you need to determine your eigenvalues. When you determine your eigenvalues, you have to plug them to solve for your eigenvectors. Then, depending on the number of eigenvalues and eigenvectors you get, you now have to put them into the form. Let's say for a 2 by 2 system, then the solution of your system is going to be c1 exponential lambda 1, okay, Then you now have your first eigenvector exponential lambda 1 t, sorry, then your first eigenvector, then plus c2 exponential second eigenvalue t, then second eigenvector, which is what? Your v2. So this is going to be the solution of your system. So these are the steps: eigenvalues, eigenvectors, then you now plug the eigenvalues and eigenvectors into the system like this, and you try to resolve it and simplify it to a good standing point. So if you do this, you'll be able to obtain the solution of any system x dot of t is equal to ax, like this. Just like we're given an I dot of t and a v dot of t is equal to some state matrix A, then you now have I of t and v of t. So this brings us to the end of this problem. I hope you like this video. Subscribe to my channel. If you have any questions, leave it in the comment section, and I'll see you in another video. Okay, bye then.